In this session, we will solve a few previous year problems on pericyclic reactions. The first problem here is the major product formed by the photochemical reaction of 2E4Z6E decatriene. We need to first write this molecule here. This is a decan system with the 3 double bonds, and the geometry of the double bonds is given here. 2E, the double bond at the second position is a trans double band, and if you start numbering from this end, it would take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is double bond at the position second. It must be a trans as it is given here, and the double bond at the fourth position is cis 4Z and 6E. A trans double bond is written here, and you must be doing this photochemical product with this substrate is we need to do either the ring closing or ring opening reactions with this substrate. Now this would become possible to do a ring closing reaction with this substrate. For doing ring closing reactions with this kind of a substrate, we need to follow this set of rules framed by Woodward and Hofmann and do electrocyclic ring closing, ring opening reaction. In this case, we have 6 pi electrons. If we take the double bond electrons, conjugated double bond electrons, it will become 6 electrons, 2 electrons here, 2 there, 2 there, and it will become 6 electrons. 6 electron system would become an example of a 4n plus 2 system. If you just give n is equal to 1, it will become 6. Now we have this 6 electron system under photochemical conditions. Now we can close this conjugated system in a conrotation fashion. This conrotation is closing the ring by rotating the terminal sp2 carbons in the same direction. What is shown here is now we need to rotate the terminal carbon here, or the substituents attached to the terminal carbons in a anti-clockwise direction, and these two terminals also must be rotated in the anti-clockwise direction. Then this would become the conrotation. Or if you do one in this direction and one in this direction, then is anti-clockwise, other one the clockwise, then it will become the disrotation. But what is required here is we need to do this and in a conrotation fashion, because only this condition is allowed according to the Woodward-Hofmann rules. A 4m plus 2 system under photochemical conditions must be either closed or opened through conrotation. So we will follow the conrotation for closing this pi electron system under photochemical conditions. Now when you rotate the substituents as shown in this direction, then this substituent will go up and this will go down. Do the same thing here. The two substituents, rotate it, and this would go up, and this will come, methyl will come down. So in the product, methyl has come down and the substituent is gone up. In addition to that, the pi electrons would get reorganized. These pi electrons will go to here and make a bond, and these pi electrons will move here, makes it double bond, and this would come here, makes it double bond. This is a new sigma bond formed between this carbon and this carbon, and these are the two pi bonds which is moved here, and this pi bond has moved here, that is shown here. So the answer for this question is option 1. The major product formed in the following reaction is this is substrate given under thermal conditions or at 150 degree centigrade. You need to heat this molecule. So this would become an example of intermolecular diol-Saldar reaction, where we have both the diene, a diene is there, a conjugated diene is there, a dienephyl is there. This is a dienephyl which is activated, alkene is there. Now we need to do the cycloaddition reaction, intramolecular cycloaddition. Same thing is written here, and the same molecule is written like this so as to bring the reacting centers close to each other. In writing like this, we need to maintain the double bond geometry. There should not be any changes in the double bond geometry. Look at this double bond. This double bond is a trans double bond. So the same trans geometry is maintained here, and this double bond also is a trans double bond. The same geometry is maintained here, and these are the pi electron reorganization, and this pi electrons will make bond with this carbon, and this pi electrons will make bond with this carbon, and this pi electrons would move here, makes it a double bond. That is what is shown here. And what also is shown here is the COET group and hydrogen. Here they are cis to each other and below the plane, because they need to write the product, the endo product is favored in this case because of the secondary orbital interactions. Because of the endo product, the major product will be endo product. If you have written the COAT group and H below the plane. And must also be knowing here that diel reaction is stereo specific. Stereo specific means the double bond geometry is maintained in the product. Here the double bond geometry is trans, and the substituent here is one more hydrogen. This hydrogen and COET group, they are cis to each other. One more hydrogen is there. These two are cis to each other. The same relation must be maintained in the product. As this would go below the plane, this hydrogen, what is shown here is above the plane, and this must again be above the plane because these two are trans here, and these two must also be trans here. This CH2 group, and this hydrogen here is cis2, the COIT group, that is also shown as COIT group, cis2 COIT group. And one more hydrogen you can find here. This is inside the ring system or inside the conjugated system. The substitute which is inside the conjugated system will go above the plane, and this substituent is away from the conjugated system. That's how that would go below the plane. That's how this is written, and this would now matches with the option 1. What is very important is we need to maintain the stereo specificity, endo selectivity, and the groups which are at the terminal carbons, the position of the groups at the terminal carbons of the diene system, their position must be known. And the other problem is the major product formed in the following reaction is this is given substrate under with this reagent potassium hydride. It is a strong base and diglycine solvent at 110 degrees centigrade. Now the same product is written here like this and is again written like this so as to be in a approximately a 6-membered chair form. And we maintain, while writing this, we maintain the geometry of the double bond. The geometry of the double bond is given here a trans geometry is maintained, and this is the cis. This geometry is maintained here, and we have written the two substituents OH and OMe present in the substrate. This OH is now slightly in the equatorially up, and this is equatorially down because the equatorial positions are stable. So we have just maintained the positions of the OH substituents as is given in the substrates and maintained the double bond geometry. And this system is written slightly in a 6-membered chair form. And now the electrons would get reorganized like this. So this would become an example of 1,5 sigmatrophic rearrangement reaction, because in any given substrate, if there is a 1,5 diene is there, then we can do 3,3 sigmatrophic reactions. And this is an example of having you 1,5 diene. If start numbering from one of the sp2 carbons, 1, 2, 3, 4, 5, 6. So the position of the double bonds will be at 1 and 5. So this will be taken as 1,5 diene system. With 1,5 diene system, we can do 3,3 sigmatrophic rearrangement reaction. For doing 3,3 sigmatrophic rearrangement reaction, how do we number the given substrate is? We should start numbering the terminal sp2 carbons 3 and 3. So this is these two are the terminal sp2 carbons in the system. So this would take the number 3. This would take number 3 again, and 2, 1, 3, 2, 1. That's how we should name the 1,5 diene system for doing 3,3 sigmatrophic rearrangement reaction. The terminal sp2 carbons are given numbers 3, 3. Then it takes 2, this takes 1. This takes 2, this takes 1. Then we need to make the bond between the numbers, the carbons numbered 3 and 3, and break the bond between the carbons numbered 1 and 1. Then this pi electrons will move here, make a double bond, and this pi electrons will move here, makes a double bond. Then this sigma bond would come here, make this double bond. That is what is shown here. And this pi electrons going there, and these are moving here. Then this sigma bond electrons are coming here, making it double bond. While doing so, we, as I already told you, the double bond geometry is maintained here. This is a trans double bond. This is a trans double bond. While writing the trans double bond, we made the methyl group equatorially below. While writing in the a 6-membered chair form, we maintained the double bond geometry, and also we maintain the methyl must be approximately equal below the equatorially below, and this hydrogen you could see here is equatorially above, and this methyl is equatorially below. When you make the bond, then this hydrogen will become above and this methyl will become below the plane. That's what is shown here. And also, as this is below the plane, as it is moving here like this, a trans double bond is formed here. So this product would match with the option 3. And in the next example, or in the next problem, the following transformation involves sequential rearrangement reaction. What are the sequential reactions it would involve to go from here to here? This is the given substrate, and this is the product formed here. We need to go through a set of reactions to come from here to here. First, we need to identify the set of reactions that would follow to go to this product. So looking at the substrate, what we can do is, first we find the 1,5-diene system. A 1,5-diene system, we need to search whether these two double bonds will become a 1,5-diene system, whether these two double bonds will become 1,5-diene system. Then we will think of doing 3,3 sigma-trophic rearrangement reaction. Now if you start coming from here, 1, 2, 3, 4, 5, 6. So this would become an example of 1,5-diene system because the position of the double bonds will be 1 and 5. And if you do numbering from this end or this end and going through like this, takes 1, 2, 3, 4, 5, 6. The position of double bonds are not at the 1, 5, they are at 1, 6 positions. So now we should start with the 1,5-diene system doing 3,3 sigma-trophic rearrangement reaction. So this system will become an example of 1,5-diene system. 1, 2, 3, 4, 5. 1,5-diene system. So with 1,5-diene system, we can do 3,3 sigma-trophic rearrangement reaction. That rearrangement reaction is called as Cope rearrangement reaction. And for doing this Cope rearrangement reaction, I'll just have rotated this sigma 1 by 180 degree and brought this methyl which is away from this methyl close to this methyl so as to have the reacting sites near to each other. So this is the, for doing the sigma-trophic reaction, we have just identified the 1,5-diene system. Then the terminal sp2 carbons must be given the numbers. This takes 3, this takes 2, this takes 1. And this terminal carbon again takes 3, 2, 1. Now break the bond between the carbons number 1 and 1. This is the bond which is between the carbons numbered 1 and 1, and make the bond between the carbons numbered 3 and so. So this pi electrons through this carbon makes bond with this carbon. Then this pi electrons would move here. Then this sigma electrons would move here, makes this double bond. That is what is shown here. Once this product is formed, again we have produced a 1,5-diene system. Now if you start numbering from this here, this end, 1, 2, 3, 4, 5. Now the position of the double bond is at 1 and 5. So we can do 3,3 sigma-trophic rearrangement reaction. But now we are doing a 3,3 sigma-trophic rearrangement reaction on a vinyl. This is the vinyl group, allyl ether. This is an example of vinyl allyl ether. This is allyl group. This is vinyl group. So when you do 3,3 sigma-trophic rearrangement reaction on this kind of system, allyl vinyl ethers, then that would become an example of Claisen rearrangement reaction. Now again give numbering to the terminal sp2 carbons 3 and 3. This takes 3, 2, 1. Now again this is also terminal sp2 carbon 3, 2, 1. Make the bond between the carbons numbered 3 and 3. And so this pi electrons will go here, and this pi electrons will come here, and this bond electrons will come here, and break the bond between the atoms numbered 1 and 2. This was the number 1, and this was also 1. 3, 2, 1, 3, 2, 1. Now we are breaking the bond between the atoms numbered 1 and 1. Then we will get this product. So we are making the bond between this carbon and this carbon, breaking it. Now we'll get this. So this has become double bond. This has become a carbonyl group is generated. Once this is formed, this would be an example. A substrate would become a substrate for being carbonyl yin reaction. For carbonyl yin reaction, we should do, and this action will abstract this proton Here CH3 is there, that CH3 is written like this, and this bond electrons will come here, makes it double bond, and this pi electrons through this carbon will go to this carbon and make the bond, and by doing so, we have produced a OH group here. And now for coming here to here, now this is the co-rearrangement reaction. This is Claisen rearrangement reaction. This is carbonyl ene reaction. So the set of reactions which must be followed in order is co-rearrangement, Claisen rearrangement, and ene reaction. So in this problem, the following transformation proceeds through two consecutive electrocyclic processes, which are we need to identify the processes through which we can go from here to here. As I already told you, you need to follow the set of rules framed by Woodward and Hofmann for doing electrocyclic ring closing or ring opening reactions. Now, for a system with 4n electrons under thermal conditions, we can either close the ring or open the ring in a Kahn rotation. Whatever given is, these are the allowed set of rules. And a 4n electron system under photochemical conditions must be either closed or opened in a this rotation fashion. Then for a 4n plus system under thermal conditions, it must be done through this rotation. This is allowed. Whatever given is, there are the allowed conditions. A 4n plus system under photochemical conditions must be either closed or opened through current rotation. Now, for going from here to here, we need to do two processes. One, we should first open this 4-membered ringer, then we should close the resultant molecule produced. Now, for opening this ring, as we know that these pi electrons are delocalized, this could be written like this. Then this system will, this is the 4-membered ring. We should open this ring. How do we open? So in this case, for ring opening reaction, in addition to the pi electron, we should take two sigma electrons. So this is the bond we need to break so as to open this ring, and 2 electrons from here, 2 sigma electrons and 2 pi electrons makes it a pi electron system. And we need to open this ring by 4 pi. In what fashion we should open is a 4 electron system under thermal conditions. Under thermal condition, in a Kahn rotation way, we should open this. For that, as there is no substituents, here we can do directly without paying attention to the orientation substitutes in the product. Now this would come here, the sigma electrons makes a double bond, and this pi electrons will move here, makes this double bond. That is what is shown here. Then this substrate is written here so as to bring all the terminal sp2 carbon near to this to do the electrocyclic ring closing reaction further. Now, the same thing is written here in this form. Now, we should consider this conjugated system. So, here we have 6 pi electrons. 6 pi electrons is an example of 4n plus 2. 4n plus 2 under thermal condition. In a dis rotation fashion, we should close the ring. So, this pi electrons will go here, and this pi electrons will go here, and this pi electrons will come here, makes this double bond, and this is the product produced. And we don't have to pay attention to the kind of a substituents, their orientation at the terminal sp2 carbons, because the substitute here is both hydrogen, here also is both hydrogens. So for coming here to here, first we need to open the 4-membered ring, then close the then we should make the ring using this 6 pi electrons in a dis rotation fashion. A 4 pi electron system must be opened Kahn rotatory, and 6 pi electron system must be closed dis rotation. So this would be the answer for this. The other problem here is the major products A and B formed in the following sequence are. This is the given substrate. Under these conditions, diethyl malleate peroxyl acetonate gives compound A, and this, when treated with the diethyl acetylene dicarboxylate, will give 3. In the first step, what is produced is a nitrogen intermediate is produced. That nitrogen intermediate is added to the diethyl malleate in a stereospecific manner. Then that would be taken to diethyl acetylene dicarboxylate doing cyclo addition reaction to give the product B. Now we'll go here, and as nitrogen is produced, this would add to the a carbon-carbon double bond in a stereo-specific manner. The stereo-specific manner is both the substitute here they are cis to each other and they maintain cis to each other. Once this is formed, a three-membered ring azidine is formed, and under thermal conditions, a 4n thermal conrotation, we should open this three-membered ring under thermal conditions. As no condition is provided, it is taken as thermal conditions in a conrotation fashion. If how does it become the 4-electron system? We need to consider the sigma electrons and two lone pair of electrons present in the nitrogen. So total it is 4 electrons for ring opening of this system. Then a 4-pi system under thermal conditions must be opened in a conrotation fashion. The conrotation is rotating the substrates of the terminal the carbons in the same direction. So if you rotate this carbon or the substitute this carbon in a clockwise, then this must also be rotated in a clockwise. So this COAT group goes away from this system and COAT groups inside of this system. So this is what is produced here. Once this is produced, it can be taken to 1,3 dipolar intermediate, and as diethyl acetylene dicarboxylate when is treated with this pi electrons will make bond with here, and this electrons will again make bond here in this system. While doing so, these are the substituents which are inside of the chain which could undergo the cycloaddition reaction. Then these two will go up, these two will come down. That is what is shown here. So the product formed here is the option 1. Now what we could see is the stereo-specific addition of a nitrogen to a carbon-carbon double bond, and also as this COAT group and COAT group, one is below the plane, one is above the plane. How this happened was we opened this in a conrotation fashion. The conrotation opening would lead to this kind of orientations of COAT groups. The next problem is the major products A and B formed in the following reaction are. Now in this case, what is given is cyclopentadiene is given and vinyl phenyl sulfone is given as the substrates under thermal conditions, and we can easily see that we can do 4n plus 2 cycloaddition reaction. So this is the cyclopentadiene system and vinyl phenyl sulfone. Now this cyclopentadiene is written like this, and this is taken here, and we can do 4 plus 2 cycloaddition reaction. So these 4 electrons will go here, and this would move here, and this moves here. So that is what is produced, and we also have maintained the endo geometry, endo selectivity. So the SOPH group is written below. This is above and this is below, just to have the endo selectivity. And once this is formed, it would produce the double bond here by this oxygen abstract the cis proton, the proton which is cis to each, and thus electrons will come here, and this bond electrons will come onto sulfur. PHSOH is removed here, and double bond is produced, and this system under photochemical conditions undergo 2 plus 2 cycloaddition. So this pi electrons and this pi electrons will be taken for doing 2 plus 2 cycloaddition. This pi electrons through this carbon makes bond here, and this pi electrons make a bond here. So under photochemical conditions, what is done is a 2 plus 2 cycloaddition. Under thermal conditions, we can always do a 4 plus 2 cycloaddition reaction, because 4 plus 2 cycloaddition will be feasible here, because we need to take the suprafacial of this and suprafacial of this for doing this reaction. In case of 2 plus 2 reaction, process also through suprafacially. So under thermal conditions, we would go for 4 plus 2 cycloaddition, because it proceeds through suprafacial interactions, and under photochemical conditions, we will do 2 plus 2 cycloaddition reaction, because in this case also suprafacial interactions are favored here. So we'll get this product. So this would now match with the option 3. That's all is about this set of questions. If anything, just write to us.